Continuation of simple harmonic motion. Simple harmonic motion in which the acceleration is proportional to displacement directed towards the mean position, or we can also say force is directly proportional to displacement also directed towards the mean position. So when object is vibrating, it will undergo a simple harmonic motion if it fulfill this condition, the acceleration proportional to displacement or force proportional to displacement. The term resonance, the term resonance refers to when it object force the other object to vibrate by applying a frequency which matches with natural frequency of object. So when we force the object to vibrate by applying a natural frequency, we call this phenomena as resonance. So example, for every material, because for every object made up of different types of material, and these particles which the material is made up of, these particles having a natural frequency. What is the meaning of a natural frequency? There is a frequency of a vibration for which their amplitude is maximum. So frequency for which the amplitude is maximum, we call that frequency as natural frequency. So example, if I consider a particle vibration, say this is a particle vibration. So these particles are vibrating, but the frequency for which the amplitude of vibration is maximum, that frequency, like some particles are moving faster, some are moving slower even within the same material, but there is a frequency for which the amplitude is greater, we call that frequency as natural frequency. So for every object, for every material, there is a natural frequency of the particle. So what is the phenomena of a resonance? Resonance means when we apply a frequency which matches with the natural frequency, so object will vibrate with the maximum amplitude, and we call that as resonance. So example, if I apply example 20 hertz frequency, so the particles are vibrating, then I apply 70 hertz, and then I apply 100 hertz. And when I compare the frequency of the vibration of the particles for which the amplitude is maximum, so example at 70, they are vibrating with the maximum amplitude. So what is the natural frequency of this object or material? That natural frequency is 70 hertz. And this is also example of force vibration, when one object forces the other object to vibrate. If we sketch a graph for applied frequency and the amplitude, on y-axis the amplitude of the motion, on x-axis is the frequency, the applied frequency, the frequency which we are applying. So what will be the shape of the graph we will obtain for applying a frequency and trying to cause the object to vibrate? Because the particles are vibrating, even we did not apply any frequency, particles are in a state of motion, so it will not start from zero, it will start with a certain frequency, certain value of a frequency. any value, but even we are not applying a applied frequency is zero, but still there is a particle vibration, so there is an amplitude. As we are increasing the applied frequency, the amplitude of vibration will also increase. And then what happen, at certain frequency the amplitude of vibration is maximum. So when the amplitude of vibration is maximum, that frequency is known as resonance frequency. So frequency for which the amplitude is maximum, we call that as resonant frequency, and also known as natural frequency. Now, what is the effect of damping? This is F naught, means the frequency for which amplitude of vibration is maximum. What is the effect of damping? When we apply damping to the system, damping means we remove the energy or energies absorbed from a total value, so which gradually diminish and hence reduce the amplitude of successive cycles or vibration. So if we apply or remove the energy gradually, or a dam system is there, so what we will observe, we'll observe that the amplitude of vibration will decrease, as well as the resonance frequency for which amplitude is maximum, that will also decrease. So the shape of the graph, if it is lightly damped, what we'll observe, this will be the shape of the graph. If it is heavily damped means we are not allowing it to vibrate too much, so amplitude will be smaller. So this is for heavily damped. The first one is for undamped. The second one is for lightly damped. And the last one is representing overdamped. What is the advantage of damping or removing the energy from the system? So when we cause a damping, the resonance frequency decreases, as well as the second thing what happened, the natural frequency, the frequency for which the amplitude of the vibration is maximum, you can see that is also decreasing. So this can be used in application, the application of these dampers and the phenomena of the resonance. It can be used for a shock absorbers. How it can be used for a shock absorber? Example, or as a damper, or to protect the buildings from collapsing. For example, this is a building which is having a base, some part is underground. Due to earthquake, what happened, the earth will vibrate, and the vibration of the earth means that there is a energy transfer, or it is applying some frequency on the building. So when it is applying frequency on the building, what will happen, this building will absorb energy and it will start to vibrate. If the frequency if the frequency of the vibration due to the earthquake matches with the natural frequency of the particles, what will happen, if the resonant frequency matches with the natural frequency, we will have maximum amplitude of vibration. As we will have a maximum amplitude of vibration, then the building will collapse. So to reduce this effect, what we have in the building, we have these dampers. What are the advantages? What is the advantage of these dampers? And it is heavily damped. So first thing what they will do, they will reduce the natural frequency. So as they reduce the natural frequency, the frequency at which the wave is produced or vibration is produced by the earthquake will be higher as compared to the natural frequency. So it will not matches with the natural frequency. And second thing, even if it matches with the natural frequency, because it is a heavily damped system, it will absorb energy. As it will absorb energy, so vibration of the particle will be minimum, which make it safe or avoid this or reduce the effect of vibration on the structure of the building. Is it clear? The idea of the damping? Any doubt in this? So we will do some questions now related to the thermal physics and as well as the simple harmonic motion. The first one is from 2011 paper. Okay, question 3. I want participation from everyone. Try to participate and answer the question. In question 3, two different sized boxes P and Q contain the same number of nitrogen molecule. The molecule in box P have twice the root mean square speed of those in the box in Q. Which of the following state must be correct? Question 3 for January 2011 paper. Question 3, what could be the right answer? Both contain the two boxes, both contain the nitrogen molecules. Look, the correct answer is D. Why D is the correct answer for this? Because the root mean square, the kinetic energy and the temperature are directly proportional. And the kinetic energy is half mv square. Mass is same for both, so it means kinetic energy is proportional to the speed square because the both container are filled with nitrogen. So mass is constant. So if the speed, the root mean square is increasing, the kinetic energy increase. As the kinetic energy increase, then what will happen? The temperature will also increase. That's why the temperature of the gas in box P is greater than Q. And they mention here different size boxes. So why the pressure? You cannot compare the pressure. If you apply a pressure law, for applying a pressure law, pressure and temperature are directly proportional. But what is the condition to apply a pressure law? That the volume must be kept constant. But because there are two different size boxes, so here the volume cannot be same. Then that's why even there's an increase in temperature, but we cannot say there will be increase in pressure as well. The gravitational field strength at the surface of the Mars is one third of that of at the surface of the Earth. The spring system is there with a frequency of 3 Hertz at the surface of Earth would have a frequency at the surface of Earth. So would have a frequency at the surface of Mars of what will be the frequency on the surface of the Mars? T is equals to 2 pi under root L over G. You can compare with that. Or for mass attached to a spring, T is equals to 2 pi under root m divided by k. For a mass spring system, mass attached to a spring, T is equals to 2 pi under root m divided by k. Question 6. What could be the answer? So B is the right answer. Why B is the right answer? Because when you compare, because this is for a pendulum, this one is for the mass spring system. So mass, because mass is amount of matter that is not changing. K is a spring constant that depends on the type of spring, that does not depend on the planet. So F divide the force extension ratio will be same and other factors are same. So both will have the same frequencies. And if both have the same frequencies, both will have the same time period. Time period vary if you changes the mass. The graph below shows how a displacement vary with the time for a particle moving with undamped simple harmonic motion. So this is a displacement time graph. For each of the question from 8 to 10, which of the following graph best represent the quantity during the corresponding time interval? Each graph may be used once, more than once, or not at all. The velocity of the particle. First thing to do this question, you should check what is the function showing this displacement graph. Which function is the displacement graph? Sine, cosine, minus sine, or minus cosine? Which one is this? So it is sine because sine 0 is 0 and sine 90 is maximum. So this graph is actually representing the displacement is represented by sine. If displacement is represented by sine, when we take a derivative, so derivative of sine theta is cosine theta. And when we again take a derivative of cosine theta, it will be minus sine theta. So the question is, which of them is representing a velocity of the particle? Which graph? A, B, C, or D? Question 8. So B is, because this graph is minus sine. This one is for cosine. This one is again sine graph is there. And this one is not showing a relation sine or cosine. It's a linear graph, a linear equation graph. So B is representing a velocity. The next part they're asking acceleration of the particle. Which one is representing acceleration? So question 9. So acceleration is represented by A, because as you can see, when we take a derivative of cos, it will be minus sine. So expression velocity is denoted by B, whereas acceleration is denoted by A. And the last question, question 10, also we have to use this graph. The total energy, which graph is representing the total energy? Yeah, for 10 it is D, because the total energy of the system, it's an undamped. So if it's an undamped, the amplitude of the vibration, the energy is not dissipated. So and the total energy will remain same. It changes only from kinetic to potential. In this question, a typical aerosol can is able to withstand a pressure up to 12 atmosphere before explode. 3 exponent minus 4 meter cube aerosol contain 3 exponent 22 molecules of a gas as a propellant. Show that the pressure would reach 12 atmospheric at a temperature about 900 Kelvin. 1 atm is equals to 1 exponent 5 Pascal. So we have to use a relation, we have to use the equation. We can use PV is equals to nRT or PV is equals to nKT. The two equations which we have, the general gas constant. So the general gas equation, PV is equals to nRT. So PV is equals to nRT or PV is equals to nKT, where n is the number of the particle, k is the Boltzmann constant, t is the temperature, v is the volume, p is the pressure. And here n is the number of the moles and r is the general gas constant. So it's up to you, either, because from number of molecules you can find the moles and then multiply by general gas constant, or you can use this formula directly, because here you don't have to first find the moles, but both formulas will give the same result. So we know the pressure that is given, because when the pressure is changes to 12 atmosphere, we have to show the temperature is about 900 Kelvin. So if we need temperature, if I am using this equation, so temperature will be equal to PV divided by NK, where P is a pressure which is 12 atm, so it will be 12 into 1 exponent 5 when we convert into Pascal, multiply by volume. The volume is given 3 exponent minus 4, and divided by the number of the particle which are given 3 into 10 to the power 22, and the Boltzmann constant is 1.38 into 10 to the power minus 23. So when you multiply them, you will get the temperature. What's the answer for this when you calculate this temperature? But it should be around 900 Kelvin. So yeah, 870. So that's equal to 870 Kelvin. Then in the next part, some aerosol can containing a liquid propellant. The propellant exists inside a can as a liquid and a vapor. Explain what happened when such aerosol can is heated about 900 Kelvin. So now what we have a propellant which is a mixture which can easily be vaporized, or it is a mixture basically of liquid and gas. So what will happen for such propellant if the temperature is increased to 900 Kelvin? So because they consist of both, so they consist of both liquid and gas, so the total pressure will be higher. Like the first propellant, in the first part the propellant was having only gas particle and the temperature was 900. But now what we have a propellant which is a mixture of liquid and gas, and at 900 Kelvin, so there will be a pressure due to a liquid and there will be a pressure due to the gas particle. So what will happen, it will explode at a lower pressure, or it will explode at a lower temperature. Even before 900 Kelvin it might explode. So when we supply the heat energy, the particles will gain energy, and greater amount of gas particle or number of gas particle will also increase, because as you are supplying energy, the liquid will turn, a molecules in the liquid will turn into or liquid change to gas? So the resultant pressure will increase. Okay, in the next question, a copper wire of diameter 1.63 millimeter and a length 105 kilometer is to be melted down to sell for scrap. Show that the mass is about 2000 kilograms. So density is mass over volume. How to get the volume? If a diameter is given, first you have to convert millimeter into meter, divide by 1000 or 1.63 into 10 power minus 3 meter. That's a diameter. As it's a cylindric, a wire is there, so if I multiply to get the volume, if I multiply area with the length, I will get the volume. So area multiplied by length will get the volume, and after getting a volume, the density is given, so density is mass over volume. So the mass will be equal to density multiplied by volume. And how to get an area from diameter? Area of cross section of wire is pi r square if you have the radius, or if you want to use a diameter for this, so it will be pi d square by 4. The next part, the wire is initially at a temperature of 25 degrees centigrade and its melting point is 1085 degrees centigrade. Calculate the energy required to raise the temperature of wire to its melting point. So whenever you are finding energy supplied to change the temperature, it is specific heat you will use, or thermal capacity can also be used depending on what is given in the question. But here in the question, specific heat is given. So we'll use a specific heat formula. According to specific heat, C is equals to E divided by M delta T. So we can use E is equals to Cm delta T. Look, if you are using a temperature in the question, it should always be in Kelvin. But when you are calculating a temperature change, then it does not make a difference, because the temperature change in a Kelvin is always same as temperature change in degree centigrade. So if temperature change you have to substitute in a question, you don't have to convert the unit, it will be same. But if temperature you want to only substitute one of the temperature, then it should be in Kelvin. So energy is equals to Cm delta T. The specific heat is 385 multiplied by the mass, which we have to calculate in the previous part. I'm taking the answer from the previous 2000. And the temperature change, it is 1085 minus 25. So we will get the energy required to reach the melting point of this copper. So which will be 8 exponent 8 joules. Then what happened? Once the melting point is reached, there is no further increase in temperature until all the copper is melted. Discuss what happened to energy of the copper atom before and during the melting process. So before, what happened? Basically, when we are supplying energy, the energy was used to increase the kinetic energy. But during a melting, whenever there is a change in state, there is no change in temperature. So means the kinetic energy at a melting point is not changing, only the energy which we supply is transformed into or changed into potential energy. So before the melting point, energy was changing the kinetic energy supplied, changing the kinetic energy. But after or during the melting, the process of melting, because the temperature does not change, so kinetic energy will remain constant, and energy changes to potential energy. That's why the particle move away from each other. Observing the display of a floating image, the clock relies on a phenomena of persistence of vision. The clock has a band uh, uh, with a set of flashing light emitting diodes. At its end, the band oscillates rapidly back and forth and take about 0.0625 seconds to shift from one end to other. So it means from one place to another, it's taking 0.0625 seconds. It become invisible to the eye, and only what we see is a image which is created, or the floating image effect which is created by these LEDs. The tip is for a simple harmonic motion sweep through a distance of 10 centimeter from one end to another. Calculate the frequency. So the distance from one end to another, that is 10 centimeter. But when we take we take amplitude from mean position. So from mean position, the distance is 5 centimeter. And if we need a frequency, so we can find the time period. This is one way, finding a time period. And using a time period, we can work out the frequency in the question, or reciprocal of the time period is also a frequency. So, but what is the time period? As they mentioned, time period is a time to complete one vibration or one oscillation. So when it is going from one side to another, it was taking, according to the question, 0.0625 seconds. But as it returned, it will also take 0.0625 seconds. So the time period is actually 2 multiplied by 0.0625. So if we know the time period and frequency, they are reciprocal of each other. So it is frequency will be 1 over time period. So t multiply 1 over 0.0625. When we multiply them and take a reciprocal, the frequency will be 2 into 0.0. So that is 8 hertz. Then the next part, the speed of the band varies as it swept back and forth. At what point will the speed maximum? This is a simple harmonic motion. If you remember simple harmonic motion, acceleration is proportional to displacement. So which point it will have a maximum acceleration? It Acceleration will be maximum at the extreme position. But which position it will have a maximum speed? Here acceleration is 0, and at the midpoint or at the mean position it will have maximum speed. Calculate the maximum speed. So how we can calculate a maximum speed? So the formula which relate or which we can use to calculate the maximum speed, the maximum speed for object performing a simple harmonic motion is equals to omega, the angular velocity, into a. A is the amplitude, and omega, what is omega? Omega is equals to 2 pi f, because omega is equals to 2 pi divided by t. You can use that also, or time period is reciprocal of frequency, so it will be 2 pi f. So in place of omega, you can write 2 pi f and multiplied by amplitude. The amplitude, because the total from one end to another is 10 centimeter, so it will be, the amplitude will be 5 centimeter. So 2 multiplied by 3.14 multiplied by 8 multiplied by 5 centimeters, so 5 divided by 100, and we will solve to get the maximum speed. What's the answer for maximum speed? That's 2.51. So the maximum speed for this object which undergo a simple harmonic motion, that's 2.51 meter per second. In a normal operation, the clock may take a faint tickle or humming sound. An unstable surface supporting the clock can result in a noisy operation due to the resonance. Explain what is meant by the term resonance. So as you can see, we just discussed in the beginning the definition of the resonance. So when we define a term resonance, when one object is forcing the other object to vibrate by applying a frequency equal to the natural frequency. So the system is forced to vibrate by applying frequency which is equal to natural frequency of system, so it vibrate with maximum amplitude. This is called a phenomena of resonance. The next part, the clock is mounted on a rubber feet so that it does not make a direct contact with the surface. Explain how this helps to reduce the effect of resonance. Like this clock is placed on the rubber and then it is placed on the rubber feet is there and then it is placed on the table. So how these rubber feet, because basically rubbers can also be used as a damper because they can absorb energy, they can transform the energy into internal. Anything which can remove the energy from the system is called a damper. So rubber is actually having a damping effect, or rubber is acting like a damper. So it can absorb energy or remove the energy from a system which does not allow the system to vibrate with a maximum amplitude. Is it clear? So this was January 2011 paper. We did thermal and simple harmonic motion question.